All right, today we're going to dive into a chemical mystery that pretty much breaks one of the first rules you ever learn in chemistry class. We are talking about noble gases. You know, the elements that are supposed to be totally unreactive and the incredibly strange compounds they can actually form.
You've heard this a million times, right? Noble gases have a full shell of electrons, they're super stable, they're happy on their own, and they just don't react. It's Chemistry 101. It's literally why they're called noble. But what if that rule isn't exactly true?
Because, well, these things are very real. You're looking at xenon, a noble gas, bonded with super reactive elements like fluorine and oxygen, making totally stable molecules. So that's the big puzzle for today. How is this even possible, and why do they make these really weird shapes? Okay, let's get into it.
To really crack this paradox, we need two decoder keys. These two ideas are going to unlock everything for us. First, how xenon can even form bonds, and second, how it ends up with these very specific 3D structures.
So here's our first key, the expanded octet. The thing about xenon is it's a big atom. And because it's big, it has these empty d orbitals just kind of sitting there. Think of it like extra storage space. When a really pushy element like fluorine comes along, xenon can actually promote some of its electrons into that empty space, letting it break that sacred 8-electron octet rule. This is the secret trick that allows a noble gas to react at all.
And our second key is VSEPR theory. This is basically the rule book for how molecules get their shape. The main idea is that every pair of electrons, whether they're in a bond or just hanging out as a lone pair, really wants its own personal space. And you got to think of the lone pairs as grumpy introverts. They take up way more room and they push everybody else away, and that has a huge effect on the final shape of the molecule.
So with these two keys, we can use a really simple 3-step process to figure out the shape of any of these xenon compounds. This is the code we're going to use to crack each one of our cases, and we're starting right now.
All right, tools in hand, it's time to open our first case file. Let's talk about Xenon Tetrafluoride, or XeF4. This one is a real classic.
Okay, so check this out. XeF4 has 4 fluorines bonded to it and 2 lone pairs. That's 6 regions of electron density total. The hybridization is sp3d2, which should point to an octahedral shape. So why is the molecule a completely flat square?
So here's how it all comes together. Xenon gets a little excited and bumps 2 of its electrons up into those empty d orbitals we talk about. This mashup creates 6 identical hybrid orbitals. 4 of them are used to form bonds with fluorine atoms, and the last 2, well, they become the homes for those 2 all-important lone pairs.
And that leads us right back to the central puzzle of this molecule. I mean, if you have 6 electron groups, they all want to be as far apart as possible, right? That arrangement should be an octahedron, kind of like 2 pyramids stuck together at the base. So why on earth is this molecule totally flat? And here is the brilliant answer. That lone pair repulsion, it's the strongest force in the game. To get as far away from each other as they possibly can, those 2 lone pairs basically shoot to the opposite ends of the molecule, the top and the bottom, 180 degrees apart. This creates so much repulsive force that it literally squishes the 4 fluorine atoms into a perfect flat square right in the middle. Mystery solved.
Okay, case 1 is in the books. Now, let's move on to our next suspect, Xenon Hexafluoride, or XeF6. This one is, well, it's a bit of a rebel. It does not play by the rules of perfect symmetry. The case file on XeF6 shows 7 electron regions. You've got 6 bonds and just 1 single lone pair. This needs an even more complex hybridization, sp3d3, and the final shape isn't something clean and neat. It's called a distorted octahedron. It's pretty clear that 1 lone pair is causing all the trouble here.
And that's the key. That single lone pair isn't just sitting there minding its own business, it's what we call stereochemically active, which is just a fancy way of saying it's a bully. It's actively pushing and shoving the 6 fluorine atoms around, warping them out of that perfect octahedral shape and creating this wobbly, asymmetrical molecule. All right, on to our final and maybe most interesting case, Xenon Oxytetrafluoride, XeOF4. This time, we're throwing a new player into the mix, an oxygen atom with a double bond.
Now, what's really fascinating here is that we're back to that same sp3d2 hybridization from our first case, but this time we've got 5 bonding regions and 1 lone pair. And that new combination gives us a totally different and honestly beautiful shape, a square pyramid.
So let's picture how this is built. You've got the 4 fluorine atoms all forming a nice flat square base. Then, that powerful oxygen double bond sits right at the top. That's the peak of our pyramid. So where does our lone pair go? It sits directly opposite the oxygen, way down at the bottom, pushing those fluorines up a little bit and forming the foundation for the entire pyramid.
So, we've investigated all 3 of our suspects. Now, it's time to bring them all together for a final lineup and see what we've really learned from all this.
Looking at them all side by side, the pattern just jumps out at you. It's not just about how many atoms are attached to the xenon. It's all about the number and the placement of those grumpy lone pairs. In XeF4, 2 lone pairs cancel each other out, creating a symmetrical, nonpolar shape. In XeF6, 1 disruptive lone pair creates a distorted, polar mess. And in XeOF4, 1 very well-behaved lone pair helps create a perfect, polar square pyramid. The lone pairs are calling all the shots.
And this whole investigation leaves us with a really fascinating thought. That simple rule we all learned, noble gases are inert, well, it was wrong. And it makes you wonder, right? What other fundamental rules of chemistry are just suggestions? What other supposedly stable elements are out there just hiding a whole world of bizarre and amazing chemistry that we haven't even discovered yet?